Is a vibration dampener necessary? An engineering decision for reliability and safety, evaluating solutions to enhance mechanical system performance. Is a vibration dampener necessary? Agenda and scope, understanding mechanical vibration, common sources of vibration, what is a vibration dampener, types of vibration dampeners, when is a vibration dampener necessary, engineering benefits of using dampeners, when a dampener may not be required, case example, rotating equipment near resonance, cost versus risk consideration, conclusion and engineering recommendation. This opening slide establishes the central engineering question, whether a vibration dampener is necessary for a given system. In professional engineering practice, this is not a yes or no question answered by preference, but a structured decision based on physics, operating conditions, risk, and life cycle cost. Mechanical vibration exists in nearly all machines, but not all vibration is harmful. The purpose of this presentation is to frame vibration dampeners as engineering controls used to manage risk rather than as default components. The title encourages critical thinking by focusing on necessity, prompting engineers to evaluate system dynamics, operating speeds, excitation sources, and failure consequences. This presentation is intended for practicing engineers, reliability specialists, and technical decision-makers responsible for rotating equipment, structures, or machinery subject to dynamic loads. It sets the expectation that the discussion will balance theory with practical application, cost considerations, and real-world operating experience. By the end of the presentation, the audience should understand when a vibration dampener is technically justified, when it adds little value, and how to communicate that decision in a professional engineering context. Illustration showing a rotating machine equipped with a vibration dampener to conceptually introduce the topic. This slide outlines the structured approach used to answer the core question. First, the presentation defines mechanical vibration in engineering terms, emphasizing why it matters for reliability and safety. Next, it explains what vibration dampeners are and how they function from an energy dissipation perspective. The discussion then moves into practical criteria for determining when dampeners are necessary, including resonance, cyclic stress, and equipment sensitivity. Benefits such as fatigue life extension and reduced maintenance are weighed against situations where dampeners may be unnecessary due to sufficient stiffness or low excitation levels. A short case-style example is included to connect theory with practice, followed by a cost versus risk evaluation framework commonly used in engineering decision-making. Finally, the presentation concludes with a clear engineering recommendation mindset. This agenda reinforces that the topic will be addressed systematically rather than anecdotally, aligning with professional engineering standards and good design practice. Mechanical vibration is defined as oscillatory motion about an equilibrium position. In engineering systems, vibration arises when dynamic forces act on mass and stiffness, producing motion that repeats over time. While some vibration is unavoidable, excessive vibration can accelerate fatigue damage, loosen fasteners, degrade bearings and seals, and generate unacceptable noise. From a reliability standpoint, vibration is one of the most common precursors to mechanical failure. Engineers must consider vibration amplitude, frequency, and duration, as each affects components differently. Low amplitude, high-frequency vibration may damage electronics, while high-amplitude, low-frequency vibration may cause structural cracking. Understanding vibration as a physical phenomenon is essential before deciding on mitigation methods. This slide emphasizes that vibration itself is not inherently bad, rather, it becomes a problem when it exceeds allowable limits defined by design codes, standards, or equipment manufacturer recommendations. Conceptual frequency response illustration showing how vibration amplitude varies with excitation frequency. This slide identifies typical sources of vibration encountered in engineering systems. Unbalance occurs when mass is unevenly distributed around a rotating axis, generating centrifugal forces. Misalignment between shafts, couplings, or bearings introduces cyclic loads that excite vibration at running speed and harmonics. Resonance is a particularly critical condition that occurs when excitation frequency aligns with a system's natural frequency, resulting in large vibration amplitudes. External excitation sources such as flow-induced vibration, ground motion, or adjacent machinery can also transmit energy into a system. Recognizing these sources allows engineers to distinguish between root causes that should be corrected directly and symptoms that may be managed with damping. This distinction is essential, as dampeners should not be used to mask correctable design or installation flaws. A vibration dampener is a device or material designed to dissipate vibratory energy, reducing motion amplitude and dynamic stress. Unlike stiffness-based solutions that shift natural frequencies, dampeners primarily work by converting mechanical energy into heat through material deformation or fluid shear. From an engineering perspective, damping increases system stability and reduces resonance amplification. Dampeners do not eliminate vibration entirely but control it to acceptable levels. This slide explains damping using fundamental dynamic system concepts such as mass, stiffness, and damping coefficient. Understanding this mechanism helps engineers select appropriate dampening strategies and avoid unrealistic expectations about performance. Properly applied, dampeners complement good design rather than replace it. Illustration of a viscoelastic dampener concept, showing energy dissipation through material deformation. This slide reviews common categories of vibration dampeners used in engineering practice. Elastomeric dampeners use rubber or polymer materials to absorb energy and are widely used due to simplicity and cost-effectiveness. Tuned mass dampeners add a secondary mass designed to counteract vibration at specific frequencies, commonly used in structures and precision machinery. Viscous dampeners rely on fluid shear to dissipate energy and are effective over broader frequency ranges. Each type has advantages and limitations related to temperature sensitivity, maintenance, frequency dependence, and installation constraints. Engineers must match dampener type to the dominant vibration characteristics of the system. This reinforces that dampener selection is an engineering design activity, not a one-size-fits-all choice. This slide addresses the core decision criteria. A vibration dampener is generally necessary when a system operates near its natural frequency, where resonance can amplify stresses dramatically. High cyclic stresses that approach fatigue limits also justify damping to extend component life. Dampeners are often required for sensitive equipment where even small vibrations affect performance, accuracy, or safety. Regulatory requirements, industry standards, or manufacturer specifications may explicitly mandate vibration control. Importantly, necessity is defined by risk, the likelihood of failure multiplied by consequence. Engineers should document these conditions clearly when recommending dampeners to ensure defensible and traceable design decisions. The benefits of vibration dampeners are best expressed in engineering outcomes. Reduced vibration amplitude lowers alternating stress, directly improving fatigue life of shafts, welds, and fasteners. Bearings and seals benefit from smoother operation, reducing heat generation and wear. Lower vibration also improves safety by reducing the risk of catastrophic failure and secondary damage. From a maintenance perspective, dampeners can decrease inspection frequency, unplanned downtime, and spare parts consumption. This slide emphasizes that these benefits are realized only when dampeners are correctly specified, installed, and maintained as part of an overall vibration management strategy. Not all systems require vibration dampeners, and unnecessary use can add cost and complexity. If measured vibration levels are well below allowable limits, damping may provide little additional benefit. Systems with high structural stiffness and adequate separation from resonance may inherently control vibration. In some cases, sufficient fatigue margin exists even under dynamic loading. This slide reinforces that good engineering includes knowing when not to add components. Overdesign can introduce new failure modes, such as dampener degradation or maintenance oversight. Engineers should rely on data, analysis, and standards rather than assumptions. This slide presents a simplified case example of rotating equipment operating near a natural frequency. As operating speed approaches resonance, vibration amplitudes increase sharply, leading to elevated bearing loads and fatigue stress. In such cases, redesigning stiffness or operating speed may be impractical. Adding a properly designed vibration dampener reduces peak response and stabilizes operation. This example illustrates how dampeners are often used as risk mitigation tools when other design changes are constrained by cost, schedule, or physical limitations. The case reinforces the importance of dynamic analysis in identifying resonance conditions. Engineering decisions must balance cost against risk. This slide explains how to compare the cost of a vibration dampener with the potential cost of failure, including downtime, repairs, safety incidents, and reputational impact. A relatively low-cost dampener may be justified if failure consequences are severe, even when failure probability is moderate. Conversely, high-cost damping solutions may not be justified for low-risk systems. This structured evaluation aligns with asset management and reliability engineering principles. Documenting this analysis supports transparent and defensible recommendations to stakeholders. The conclusion reinforces the central message: vibration dampeners are not universally required, but they are essential in specific conditions where vibration threatens reliability, safety, or performance. Engineers should base the decision on vibration characteristics, resonance risk, fatigue considerations, and consequence of failure. Dampeners should complement, not replace, good design and maintenance practices. The final recommendation encourages engineers to apply analytical thinking, measurement, and professional judgment when answering the question, is a vibration dampener necessary? This mindset supports robust, efficient, and defensible engineering solutions.